and we'll be talking about sequences and something you talked about back in Calc 2. For some of you, I guess that might have been quite a while ago. And let's start with a definition. A sequence of real numbers is a function defined on the set of natural numbers whose range is the set of real numbers. And you probably never thought of it that way back in Calc 2, but it mainly means, for every natural number, you're going to have a real number associated with it, was kind of what you did back in Calc 2. And so
would it just be defining the set of natural numbers whose codomain is the real numbers? Because it doesn't necessarily have to hit every real number.
That's
right?
true. Yeah, that's true. Yes, that's right. That's interesting. Yeah, that's interesting. I got this definition from a book, and you're right. That's not quite accurate. This really should say, yeah, is because it's the way they state it's the set of real numbers. Really, it should be,
Or like whose range is a subset of real
that's right.
numbers.
That's right. Yeah, that's right. Yeah, this isn't quite that isn't really accurate. That's right. Yeah, probably that would be a little bit better way to say it, is a subset, if you want to be a lot more accurate. Yeah, thanks for noticing that. That really should be a subset of real numbers. Or like you said, you could also say the codomain would work as well. Yeah, that's right. And so and then normally now, a lot of times when we'll represent sequences and every book is kind of different. It's often represented by like a parentheses and an N, or sometimes maybe a capital X. And real analysis books often use this notation, but sometimes they use other notations. So that's kind of, but you'll kind of know from the context what it is. And some examples are ones that, again, you've done in Calc 2. So you could have like something like this is a sequence, you could represent it that way. Or if you can find the actual sequence, how it's represented, the formula, like say for this would be like n to the n. So you can see this would be like 1 to the first power, 2 to the second power, 3 to the third power, etc. Or you could have something like this, one we've seen before already, is a half, a third, a quarter, or xn equal 1 over n, like this. Or you can have a sequence like this, where They're all the same. Technically, that's a sequence. The main idea, though, is you have to have a real number for every natural number. So in other words, it goes on forever. Sequences i.e. for every natural number, there is a real number. And like I said, even if it repeats, or of course, you remember from Calc 2, a lot of times they would not repeat, then eventually converge to something and just go on and on and on. So you could have ones like this. And then also, and here's the formal definition. Again, this is something that you did in Calc 2. I'm not sure how formally you might have done this, but let's do this definition here. Sequence. Again, don't worry too much about the notation. Just be aware that different books use different notations. Sometimes they'll say it like this. In the reals, again, I'll just put R for the reals. Again, where it means kind of the output, or like we were saying, the codomain is in the reals, is said to converge to X in the reals, or X is said to be the limit of the sequence. Again, maybe if you represent it this way, if for every epsilon greater than 0, there exists, I'll use the notation we've been using, a number, and I should say, really should say a natural number, and now you don't have to do this. Sometimes you can put like that. This natural number depends on the epsilon. Again, you don't have to do that. Probably a lot of times we won't, but just for the definition, you can say it depends on the epsilon, such that for all n greater than that natural number, the terms satisfy xn minus xn less than epsilon. So let's think, again, I'm not sure how much you might have done this in Calc 2 if you actually got into this, but the idea is if something converges, something has a limit. So if you have this sequence, and x said to be a limit of xn, if for every epsilon, so no matter how small you make your epsilon, there's going to be a point at which all the members of the sequence beyond that point fall within that tiny epsilon range. And maybe if you looked at, like, say, a picture, so here's your limit x right here. And if you picked an epsilon, And again, remember what this is going to indicate. This is going to indicate sort of what they sometimes call a neighborhood, like this, where this is going to be X plus epsilon and X minus epsilon. So you have your sequence, they could be points, they could be falling, somewhere around here. Then they start getting closer and closer to X. So if it truly converges to that X, then again, there'll be a point in your sequence that if, first of all, okay, pick your epsilon, whatever it is, then you can always find the natural number n so that all the members of that sequence beyond that n will all fall within that small neighborhood. Does that make sense to everyone? That's kind of the formal definition of the limit. And then if you picked a different tinier epsilon, now that's why, again, usually I don't do this, but again, why I've got this definition, they kind of put this epsilon here to emphasize that this natural number that you pick is dependent upon the epsilon. So obviously, when you get to a tinier epsilon, that capital N will be farther out, if that makes sense. Any questions on that so far? So, and then if a sequence has a limit, we say that the sequence is convergent. If it has no limit, we say that it is divergent. So again, if it has a limit, it's convergent. And if it doesn't have a limit, divergent. So divergent doesn't, when you think of something divergent, you might think it's just going to go off forever and ever, maybe get super big. And that could be that's one of the ways it could be divergent. But it could also be divergent. Let's say if your sequence just jumps between -1 and 1, that would technically be divergent too, if even though it's not getting bigger or anything. So like, for example, well, let me do a couple things. Actually, the sequence, how did I write it before? Like, say, if we just do X equal N is divergent. Because the terms of the sequence just getting bigger and bigger and bigger, and that's just going to go off. And that's so it could be it's divergent that way. But the main thing, it doesn't have a limit. Or another way it could be divergent, like I said, if you have something like this, -1 to the n. Of course, what is that going to be for n equal 1? It's going to be -1, 1, -1, 1, -1. That's also divergent. So, because sometimes the word diverge makes you think it's just going to always go up forever, but not necessarily. Just means it just doesn't have a limit in this context. And we won't prove it, maybe later. But the limits are unique, which is probably pretty obvious, but sequence in the reals. And I think the reason we say like we're specifying like that the codomain is the reals, or they'll just say a sequence in the reals, is because you could, I suppose you could have sequences in other things. I'm not sure you could really have them in complex numbers. I guess you do in some way, but in any case, so everything we're going to be dealing with is the real numbers have at most one limit. So if the limit exists, it only is one limit. Now, a little bit later, we'll be talking about subsequences where you could pull out, like say for this sequence we had here, -1, 1, -1, you pull out a subsequence, and one of them would converge to 1, the other one converge to -1. But any sequence itself that has a limit is just going to have 1. And so let me actually let me kind of show it. This is kind of hard to start, like how to prove it when you're first learning it. Let me sort of say it this way. So prove that the limit as n approaches infinity of 4 over n is 0. We're going to try to prove this. And actually, I'm going to sort of write out the proof, but then in a few minutes, we'll kind of learn how to figure out how to set up proofs like this. So again, the proofs will kind of start like this. Because we want it to work for any epsilon, we're going to say let, and that's kind of thing we always do. We want to pick something arbitrary. We'll just say let epsilon be greater than 0. And then we're going to choose our natural number, that n of e that they had in the definition. But I'm going to leave off the n of e. Choose 4 over epsilon. Then n greater than that n implies, and again, remember what we wanted to do. We wanted to have x n minus n, excuse me, minus x. We want that to be less than epsilon. On one thing I maybe should do here is, and this is something that we can maybe introduce right now. Notice this is probably not going to be a natural number. So usually what we do, we put this hat on it, and that means the next higher whole number. Just to make it, just so we end up having a number. Obviously, this epsilon is greater than 0, 4 is greater than 0, so this is going to be positive, and then that would just go to the next one. So in any case, so remember, according to our definition, what we have to show is for any epsilon greater than 0, there's an n such that for all natural numbers greater than that n, we get this less than epsilon. So let's plug everything in. So over here, we have this. We're claiming the limit is 0. And then this is going to be 4 over n. And since these are all positive numbers, I can drop the absolute value. And this is going to be 4 over N. And now since N is greater than capital N, that means if we put it, but N's in the denominator, that means it's going to be less than 4 over the capital N, which was 4 over epsilon. And then this is what, let me put all the steps in. 4 epsilon over 4 equal epsilon. So x over N minus x is less than epsilon, like that. And so the idea, once again, the idea here is, according to the definition, for all epsilon greater than 0, there exists an N such that whenever your members of your sequence is within epsilon of that limit, and we're claiming, like, say here, the limit is 0. And so maybe I should note that somewhere where this is the limit, which is 0. We have this. And so the main feature of this, we let epsilon greater than 0, and then we can find an N such that this is always less than that. See if you have any questions on that. See if that all makes sense. But now we'll, in a minute here, we'll kind of find, well, how did we know to pick this and this value here? We'll find out in a minute how to do that. But take a look, see if you have any questions so far. And of course, this step right here, since N is greater than, small n is greater than capital N, and capital N was this, if we put in the denominator, of course, it becomes less than that. We get that. Any questions? Okay, so let's go and let's sort of work out how we found that, or how we could find that. So let me put this up here. So let me do this example. It's almost the same. So show, a lot of times if it says show or prove that the limit as n goes to infinity, 1 over n is equal to 0. So a lot of times we do, and this is maybe like what you can sometimes call scratch work before you actually write out the proof. So think of what we're trying to do. We want our xn, and I'm going to call the limit L this time, because that makes it a little bit easier. So I'm going to call it, rather, because before in the definition had X, but I'm going to put L so that we can maybe just see this a little bit better. So we want the xn minus L to be less than epsilon, so we're going to pick an epsilon. So, say we've picked, maybe you can say up here, you're picking an epsilon. I don't know if you want to say that. And we want to try to get to this point. So in our case, our sequence is represented by 1 over n, and we want the limit to be 0, or we want to prove that it's 0. And so let's kind of work with this. Again, since it's the absolute value, we can drop the, since it's positive, we can drop the absolute value signs. So we have something like this. So now we want to find our our capital N. So we want to figure out what N is going to make this work. So what capital N will make this work? And so we're doing this, and then just rewrite this. And we can say cross multiply, have this. Or you want to write it a little bit nicer, make N greater than 1 over epsilon, like this. So this will be our capital N. That is N will be equal 1 over epsilon. Then we'll put a little hat over it like this. So this is kind of our scratch work to figure out what our capital N would be. We said, for any arbitrary epsilon, this is what we're kind of shooting for. We want this. And then we're trying to prove that the limit is 0. So we'll put that in for our limit. And this is our sequence. And see, okay, what's going to make this? So we're trying to achieve this to be less than epsilon, just like you do for any other equation. What are you going to need to make this happen? We're going to need N to be greater than 1 over epsilon. And then that's going to eventually be our capital N that we're going to choose. Any question on that so far? So then let's go ahead and write our proof. So this was kind of the scratch work to see what we wanted to get to, and then we can write our formal proof. And so proof, let epsilon be greater than 0. And then now we're going to choose, see what we had up here. We decide we're going to choose our N to be 1 over epsilon, like that. Then you'd say some of these parts, you can write them in different ways. Then for N greater than capital N, or for all N greater than capital N, even if you leave off the for all, the greater than E implies that. X. And once again, I'm going to put L here rather than X, because that's maybe a little bit more descriptive, saying that that's the limit. And once again, you don't have to put all these steps in. I'm just doing it at the beginning to kind of show what you have. And once again, because small n is greater than N, that means small n is greater than 1 over epsilon. But when you put in the denominator, that makes it going to be a less than here, and then do the reciprocal and have that. Or if you wanted to make it nicer, if you want to put down here at the bottom, you don't have to do this part because you've kind of shown it here or this. So once again, what the proof consists of, we took an arbitrary epsilon and was able to pick a capital N such that if you take members of the sequence greater than that capital N, they're all going to fall within the epsilon. Any questions on that? That's kind of a formal way to kind of show the proof of that. So the proofs, let me just, so the final proof then, so whenever we do a proof, for convergence. It should be in this form or something similar. Let epsilon be greater than 0, then choose your n, and then show what that is. And like I said, usually when I put the hat on to say, because it's the next biggest interval, so choose your n here, then for all n greater than n, and here you can say we have, sometimes they'll say we have xn minus L, and then you can put your stuff in, and then, somewhere along here, show that you have to show that that's less than epsilon. So again, just holler if you have any questions on any of that. And let's do another one here. Show that. This is true. So again, we'll do our scratch work. And, so we're going to say pick an epsilon. We want, say, this 1 over x, and like this, minus 0 to be less than epsilon. And let's see here, this time, now if we just worked with this, again, these are all going to be positive, so I can get rid of this. This is going to get kind of messy if we tried to work just with the n squared. So see if we can show what we have here is less, the epsilon. Another way to work with this is we can shoot for something that is bigger than this, that's always going to be bigger than this, and it would be less than epsilon. I don't know if I said that right. So in other words, what I want to try to say is, and maybe I should write this down, so we have x plus 1. Now, 1 is always positive, and it's added to the denominator. So if we take that away, if we take the 1 away, we'll get something bigger, huh? Okay, are we allowed to say that? Excuse me, let me keep the square first of all. We allowed to say that. Because remember, whenever the denominator is bigger, it makes the fraction smaller. So if we take a positive number away, now if this was a negative number, we couldn't do that. But this is positive, so we can take that away and get something bigger. Now, can we say, remembering that n is a natural number, could we say that that is true? I see yeses. That's right, because it's really a square. Again, if it was something less than 1, we couldn't say that. we're dealing with natural number 1 or bigger, it's always going to be the case that n squared is bigger than n, therefore the reciprocal is smaller. So we can say that. So now, so we can shoot for here, instead of trying to do this directly, which would get really messy, we're going to try to bound something bigger, because if epsilon is bigger than this, and that's bigger than that, then epsilon is bigger than this. So we'll work with this right here. And let me just write that down. With 1 over n. And once again, it's going to be the same deal as before. We're going to end up with 1 over epsilon is less than n, or n is less than 1 over epsilon. So we're going to choose our capital N to be 1 over epsilon like this. So that was our scratch work. And then, so now we do the proof. We're kind of going to go backwards. We're going to need to more or less use all these same steps to work backwards. We do the proof. So proof, once again, start with let me move this up a little bit here. Let epsilon be greater than 0. And then choose our n to be 1 over epsilon. Then for all n that is greater than that n that we chose, xn, again, you don't really need to put this in. A lot of times books won't put that in. I'm just putting it in. But you can actually start over here with the sequence itself. You could start right here. You don't need this part, as long as everyone knows what you're doing, like this. And then we're going to kind of follow almost the same step, because we need to show that this is going to be less than epsilon. So once again, we can say, and again, you can do this in 1 step, but I'm going to do it in 2 steps just so it's clear. So if we take away the 1, we can say, sorry about that, that should be less than. And if we, again, do an n, we can say this. And since n is bigger than capital N, that means that 1 over n is smaller than 1 over capital N, which is 1 over epsilon, which is equal to epsilon. So then finally, you can, and I'm going to just leave it there, because a lot of times, if you see this in books, that's the way they'll do it. They'll kind of start with the sequence minus the limit and just show that the chain gives you less than epsilon. Up a little bit. See if you have any questions on any of that. See if it all makes sense. Yes, sir.
How can we say that 1 over n squared and 1 over n is less than epsilon?
Let's see, okay, so 1 over n squared, so like and then you asked about this step
So
for
in the scratch work, well, I guess it's the same kind of step, but because 1 over n squared plus 1 is like less than those other 2.
Mhm.
But how can we be sure that epsilon is greater than those other 2?
That, oh yes, okay, so in other words, yeah, so right, this, yeah, that's a good question. So this step right here, so you're going like, say, from here to here, huh? Is that true?
Yeah.
Yeah, right. So then right here, I'm going back to this here, and that says, so over here, this says that, let me put this right here. So at this step, we're saying that N is greater than capital N, but capital N is equal to this, huh? So this is gonna be equal to 1 over epsilon, or you can, let me go down here, then we can say that N, excuse me, N, small n, is greater than 1 over epsilon. Then if we take the reciprocal, or maybe it's even clearer if we, actually, this may be clearer yet. If we just cross multiply, we can say that epsilon is greater than 1 over n. That'd be another way you could think of it. So that this, so in this case, you wouldn't even need this here if you just cross multiplied. You could say, okay, 1 over n is less than epsilon. So you could actually just put that in there. That'd be another way to think. Does that make sense? Any questions on that at all? Okay, let me go through a few more here. Let me do just at least 1 or 2 more. It sounds like it's probably clear you guys are understanding it, but let me just do another one. Let's say if we don't have a limit of 0, let's take a look at this one. Yeah, let me take a look at this one. Let me take a look at this one up here. To prove this one. And so let me just start with our scratch work. This one gets just a little bit messy. And so again, we want this 7n plus 5, 8n plus 12 minus 7/8. We want that less than epsilon. So let's go ahead and work with this. And at least for a while, we may have to keep the absolute value on because we can't be sure when this is going to be positive. So let me start down here. 7n plus 5, 8n plus 12. And we're probably going to have to make a common denominator. But let me put the first step in note. So let's make a common denominator, put these two together. And so if we multiply the left fraction by 8 over 8 minus, and then let's multiply the second fraction by this first denominator. So I just mainly doing it just by brute force, just using multiplying each fraction by the other denominator. And maybe there's a quicker way to do this. And now let's put all this together. And this is going to be 56 n plus 40 minus 56 n minus 84. Denominator, we're going to have 64n plus 96. And this is going to be all we have left in the numerator is gonna be minus 44, huh? This. And then, so this is positive, and this is positive. So if we apply the absolute value, we can just make that a positive 44, I think, huh? That should be 44, 64, and plus 96. Again, keep in mind what we're shooting for. We want this less than epsilon. And much like before, we can say, okay, this is a positive value in the denominator, so we can take that away, huh? And say that this is less than 64n. And let's see, I guess we can divide these both by numerator and denominator by 4, make it just a little bit easier to work with. 16n. Okay, so now then at this point, now we want this to be true. We want this to be less than epsilon. And so, let me just write it like this. Again, you don't have to repeat this all these times that I'm doing it, but so this is going to be, if we cross multiply again, we'll end up with 11/16 epsilon less than n, like that. And so n has to be greater than 11/16 epsilon. So we're going to then pick, when we pick our capital N, it'll be 11/16 epsilon. Any questions so far? Then when you actually do your proof, let epsilon be greater than 0. Choose our n, and like I said, at some point, put the, probably right here, put the little hat on to say it's going to the next higher one. Then, like I said, you can say for n greater than 0, or they'll say for all n, excuse me, n greater than the n we picked. And then if you've kind of included your scratch work, you can probably just kind of refer to your scratch work. Or you could put maybe a few of the steps in. You can maybe say, this is going to be equal to maybe like this. 44. Again, like I said, if you include your scratch work, you can maybe do something like this. And then this is going to be less than 44, 64n equals 11/16n. And then we can say that since n is greater than capital N, we could say that this is going to be less than 11/16 epsilon. And these will cancel, then we end up with epsilon like that. So the 16 cancels here, the 11th cancels, so we have 1/1/epsilon, which is epsilon. with sequences. To show that a sequence does not converge now. Really, you can, if you want to prove it formally, a lot of times you can just prove that it does not converge to a particular value. And there's other ways that we can kind of do this in general later, but first we'll look at to show the sequence not converge to a particular value. Say X or L, whatever. I'll call it X. Realize there's sometimes I'll use L. It is enough to produce an epsilon and maybe an epsilon sub 0 such that no matter how large one can always find an n greater than n such that xn minus x is greater than that epsilon. So if you can produce an epsilon that such that no matter how large of an n you pick, you're always going to find some points of your sequence that are going to be outside that epsilon range, so to speak. So so consider this example. Show that this sequence and that pattern goes on forever, goes from 0 to 0.1, 0.1, does not converge to 0. Proof. Let's set epsilon, or we can call it epsilon naught, equal to 0.5, 0.05. Let's pick that. And the reason I picked that because notice that every other term gets 0.1 away from 0. So if we pick something smaller than that, say 0.05, then we can show that this does not converge. So set that then for all n greater than 0, there exists an n greater than that n such that xn minus 0 is equal. In fact, we can actually put even the 0.1 minus 0 is equal to 0.1, which is greater than our epsilon, which was 0.05. So the idea is we're able to find an epsilon such that no matter what capital N we pick, we can always find a small n bigger than that capital N, where a member of the sequence is 0.1, then we take 0.1 minus our proposed limit, and that's going to be greater than epsilon. So this proves this does not converge. So let's take a look at this theorem, 3.1.8, or excuse me, this, look at this definition. If X is a sequence defined this way, and if M is a given natural number, then what's called the M tail of the sequence X is the sequence X M plus 1, X M plus 2, X M plus 3, on and on like that. And so this just means the M tail is just the tail of the sequence. And so, you're cutting off a finite number of values at the beginning of the sequence, and this is kind of like the last part of the sequence. That's called the M tail of the sequence. Read point 1.9 theorem. Let X equal this sequence, then the M tail of this sequence X converges if and only if X converges. So what it really says is the kind of the end of the sequence converges if and only if the sequence itself converges. So if you need to test whether the sequence converges, you can just focus on the last part of it, so to speak. Even though the last part of it isn't infinite, it's still, but you can, in other words, you can cut off any finite terms at the beginning and just consider everything beyond that point would be a way you could do that. So let me do this one here. In the theorem, let Xn be a sequence let X be in the reals A of n is a sequence of positive real numbers with the limit an equals 0. And if for some constant c, some positive constant, and some m in the natural numbers, we have xn minus x less than or equal to c an for all n greater than or equal to m it follows that the limit of xn is equal to x. So let's think about what they're saying. So let xn be sequence of real numbers. And then if an is the sequence of positive real numbers that converge to 0, and if for some constant c and some m in the naturals, we have that xn minus x is less than can for all n greater than or equal to m, it follows that the limit of the sequence xn is x. And we'll probably use that in a little bit here. So keep that in mind. And see. So most of these were more examples. Let me do some more definitions. And this is more limit theorems. This is actually section. Section 3.2. Theorems. Another definition here. A sequence xn of real numbers is said to be bounded if there exists a real number m greater than 0 such that xn less than m for all n in the natural numbers. So the sequence is bounded mainly if all its terms are bounded. Pretty straightforward. And then 3.2.2. Convergence. Sequence. Of real numbers is bounded. So if you have a sequence that's convergent, it's automatically bounded. There's going to be some value that's bigger than all the terms in the sequence. Because again, remember, if if it converges, its tail like converges, towards the end, and really nothing in the first finite number terms can make it unbounded because they're all real numbers. You're always going to have real numbers in all your entries. So if you have 1,000,000 terms, even if you're ignoring at the beginning of the sequence, they have to be some real values. So you could never diverge. When I say, excuse me, you could never have something unbounded in your first finite number of term, because any finite number of numbers is bounded, so to speak. You could only be unbounded when you have like n getting bigger and bigger and bigger all the time towards the end. So therefore, if it's converging, it means it's converging, toward the end of the sequence, then that means it's bounded. That's not a formal proof, but that's kind of a way to think of it logically. Any questions on any of this so far? Just speak up if there are. Let me see. Some of these other theorems are kind of clear cut, so I don't want to put too much stuff down that we don't need. One thing, and you sort of did this when you did a lot of your proofs, or not proofs, but when you did a lot of sequences in Calc 2, you maybe didn't use these quite in these terms, but you use these ideas. If X is equal to the sequence Xn and Y is equal to the sequence Yn. And let me see, maybe that's 2. Let me see if I can, that 2, let's see if it's better. Is that a little bit better? It's hard to get the right spot exactly, maybe like that. If we have, these are 2 sequences here are convergent. And if Xn is less than or equal to Yn for all n in the naturals, then the limit of Xn is less or equal to the limit of Yn. Again, you sort of use a little bit this in Calc 2. The idea, if all the members of the sequence of X are smaller than Y, then the limit is going to be less or equal to the limit of the 1. They could be equal, but you can never have the limit of Xn greater than this one. And another theorem. If X equal Xn is a convergence sequence. If A is between B, so if all the terms of the sequence are between A and B, all in the natural numbers, then the limit is going to be between those numbers. Once again, pretty logical, but there's a theorem to say that if all the members of your sequence are between A and B, the limit's going to be between A and B. Pretty clear cut. And then this again is something you used in Calc 2, the squeeze theorem. Suppose X is sequence, Y is sequence, and the Cn are all sequences. Real numbers such that X in, Y in, Z in like this. For all in the natural numbers. And the limit of Xn is equal to the limit of Zn then the sequence Yn is convergent. And the limit of Xn equal limit of Yn equal limit of Zn. So again, the idea is if you have the sequences Xn and Zn, and all the terms of Yn are between those two sequences, and then the limits of these outer sequences are the same, then that forces the limit of that inner sequence to be the same as the two outer ones. That's kind of why it's called the squeeze theorem. The Yn gets squeezed inside like that. And let's see. Yeah, I'm skipping some of these that are really obvious. Yeah, so skip some of these. Let me do one more, a few more definitions here. Three 2.9 theorem. let sequence capital X X in converge to X. Yeah, but we could say let this, in other words, suppose, maybe we should, let me write this as suppose. I think the original theorem said let, but let's say suppose the sequence converges to X. Then the sequence where you have absolute value of the terms converges to the absolute value of X. That is if the limit, excuse me, if X equal the limit of Xn, then absolute value of X is equal to the limit of Xn like this. So if the limit of sequence exists and converges to X, then the limit of the absolute values of the members also converge. They converge to absolute value. Obviously, the other way is not true. Note not true that if the limit Xn equals X, then the limit X exists. So again, it's not true that the other way around, if the limit of the terms is equal to if it exists, we just say it that way. If this exists, then it does not imply that this exists. You can think of an example. Say if you consider, what do we have before? Xn equals -1, say to the n, which is going to be what, -1, 1, -1, 1, -1, etc. The limit of the absolute values of this is obviously that's going to make all of these 1, so it's going to be 1, but the limit of Xn does not exist. So going the other way, of course, doesn't work, but even going this way works. And let's go through I'll do a couple more here, then we'll. And these you did again in Calc 2, way back when. Let Xn be a sequence. Real numbers. Converges to X. And suppose that you have all positive terms. Then the sequence of square root of positive square roots converges, and the limit of that is equal to that. So if the limit exists and the terms are all positive, then the square root of the terms also have a limit, and it's going to be the square root of that. Then let me do one more here. And this is actually, again, something used, I know you used a lot in Calc 2, the ratio test. Let Xn be a sequence of positive real numbers. Such that L is the limit of the ratio if L is less than 1, then Xn converges and the limit of Xn is 0. So now it's the ratio test from Calc 2 that if you have a sequence, again, it has to be positive real numbers, and the ratio, you know, that what it in effect means is the ratio of this is really getting smaller. If the limit's less than 1, then Xn converges and the limit is 0. Any question on